The next speaker is DiVincenzo, and he's talking about where are the photons in a transmission line pulse.
Okay, thank you. It's a pleasure to come here and tell you about this story. It's a little bit related to the last talk in the sense that it has to do with quanta that are hard to measure and used to be thought to be impossible to measure, because I'm going to be talking about ECC transmission lines, and I'll be talking about, generally speaking, states of microwave fields. And it used to be that microwave fields, I mean, I recall people from optics saying that don't talk to me about photons for anything below 50 gigahertz or something like that. That's the classical world. But these very, very soft quanta, these quanta of the microwave field, of the microwave electromagnetic field, have indeed successfully been measured, and we saw it in the morning, in fact. And so this is maybe some further advances that I'm going to ask you to consider, that we may have new, quote, technologies that we can launch based on these previously impossible quanta. So I'll be talking about a particular setup, and I will kind of liven it up by having a kind of gedanken application, which is that I'll talk about the results in terms of quantum key distribution, and in fact BB84 style, in honor of Bengaluru, and where this style of cryptography was originally announced. But a lot of this will just be a sort of exploration of some facts about microwave fields and about ultra short fields, pulsed fields, that while not completely unknown, I would say were not written down or not thought through very much before, and I think contain some truly surprising facts. So before I navigate off this, I just say that this is work based on work that was started during an internship by Debjoti Biswas in the audience here during a visit to Aachen, and then finished by my PhD student there. So let me give you a sort of setting in which we will consider this. And this is, of course, from the sort of world of quantum computing, but this is by no means about quantum computing. It's about what would be considered the sort of ancillary technology, the sort of incidental machinery that you need to have assembled in order to make a quantum computer. So here's a colleague of mine in Jülich, and you see many, many of these sort of thread-like things going from top to bottom. And those are all transmission lines, and they're all intended, or they're there in order to carry signals. And in most cases, those signals are there to activate quantum gates. So they're classical things, typically, or we would say they're classical. And they're there to control the Hamiltonian of qubits, in this case, superconducting qubits. And sometimes they're there to carry signals out of the experiment, and they're the quantum measurement or the data resulting from performing a measurement on some of these qubits. But I want to just extract out one of those cables and talk about its quantum mechanics, this object which we normally talk about classically in these systems. So a transmission line. Now, a transmission line is a simple object. It has, say, a metal core, and then some insulator, and then some metal on the outside. So, it is something for, as I say, carrying radiation. I immediately introduce a model for it. And now I've had a little trouble composing this lecture because tomorrow I'm going to give a tutorial, and it's all about how you very carefully go through the analysis of electric circuits. And so today I'll pretend that I've already given that lecture and at least quote some results from that no doubt brilliant lecture, if I could travel forward in time. And say, first of all, that this is a very good model of a transmission line. See inductors and capacitors. And what's pointed out are a few of the parameters. It has, let's see, do I have that on the next slide? No, it's already a little further. There are inductors, and what's an important parameter of this transmission line is the inductance per unit length. And then there's a capacitance between the inner and the outer conductor, and that's characterized by a capacitance per unit length. And in this diagram, I've discretized that, just for conception's sake, because it makes clear that at least our simplest description of a transmission line involves dissipationless elements. And so that means there should indeed be a quantum mechanical description of this, or first a description in terms of lossless dynamics, let's say, and of which we should be able to quantize. But in a sense, my focus will also be on the left, on the instrumentation. In many of these experiments, this instrument is used, the AWG, Arbitrary Waveform Generator. Are any of you experimentalists? Not one single one. Okay, well, too bad. But you can impress your friends by going to them and telling them the things you've learned about AWGs. They are fantastic instruments, and they do what this phrase means. They will emit a pulse of arbitrary or waveform, any arbitrary function, say voltage as a function of, say, time, can be emitted, can be impressed upon the output port of this electronic instrument, and then it will travel along the transmission line. And so I've given an example. Here's a V of t, and then it will travel at the speed of light. Speed of light, or the speed in a cable, is a fraction, a fairly large fraction of the speed of light. This kind of transmission line is special because it's dispersionless, and that will indeed be very important for the things that I'm discussing. And what that means is that this waveform, I've chosen, a sort of simple square waveform, for up and then down and then finished. And this waveform will travel without distortion, without change of shape, from start to finish. And indeed, if the model is correct, then that is a perfect statement. That's there's no correction to that statement until you've corrected the model. Good. Now, the kind of questions that I'll be talking about are the following. Suppose you make such bursts of radiation. So, this is something that could be over in a few hundred picoseconds, for example, if you want to think time scales. So rather short on the scale of this story of being in the microwave band. That would put you at 10 gigahertz or something, very roughly speaking. That is, if you had a waveform that was sinusoidal with this initial form, then that would be a 10 or so gigahertz signal. But we only have one period of this square waveform. Now, when it arrives at the end, well, it'll do things, but we'd like to develop, or what I want to develop, is a photonic description of this. What is the quantum mechanical description of this very classical sounding thing? And you'd like to believe that, well, photons arrive when this voltage pulse arrives. Sounds logical. It shouldn't be, long before or long after. And given, the amplitude of this voltage pulse, how many photons are there, and what's their frequency? And I will emphasize the paradox that we arrive at here, that I will announce that, well, Planck's law is wrong. Well, I say that, of course, with a smile. That is, E equals h bar omega should not be taken too seriously in this setting. And what it means is that photons do not necessarily have a definite frequency, that they are not, in general, quanta of frequency. Some of my colleagues like to say they're quanta of action. But I'll show you what they are quanta of rather clearly as I get into the technical aspects of this work. Now, as I said, to spice this up, I'm going to then immediately discuss a sort of application, but I very much put that in quotes. But it's built on this very concrete and very heroic experiment that was done in the basement of the Physics Institute in Zurich, in the group of Andreas Wallraff. So here you see an experiment, a schematic of an experiment. It's 30 meters long, so it's in a long corridor in the basement, and it's mostly just a long pipe connecting two experimental setups. Notice there is an A and a B, Alice and Bob, and this was created to do a very fundamental test, Bell inequalities with new aspects of how loopholes are closed. So I want to do a much less philosophical thing, but a more technologically oriented thing with this setup, namely cryptography. Now, this is very much sort of, daydream cryptography. I mean, if you really want to do QKD, you use lasers and fibers and things like this, and you go many kilometers. You don't bother doing it a few tens of meters. However, this will illustrate some principles, namely of very fast rate cryptography that I think can be taken back over and borrowed into the more practical world of cryptography. Now, the amazing thing about this experiment is that, okay, it's a pipe, and throughout the entire length of this pipe, the temperature is held at 10 millikelvin or so. So in that respect, it's a very heroic experiment. There's not actually that much inside this pipe. It's just, the necessary, refrigeration schemes to make the whole thing cold. And then in the experiment, they did one transmission line. So I'm going to increase 1 to 2 in order to discuss the idea that I'd like to bring out here. And otherwise, well, Alice will get a lot simpler and Bob will get a lot more complicated in order to do this, this application. But I'll come to that somewhat later. This is a schematic of the experiment. This is the Alice setup, lots and lots of complicated quantum equipment. Here's the Bob part of the setup, 30 meters in between with not much going on, just a pipe in between. Okay, now back to this. So as I will explain tomorrow, a circuit of this form immediately implies a certain dynamics, certain mechanics. So I'm trying not to say the word quantum too much yet, because this is also something that a classical analyst would be perfectly happy doing. That is, this is an assembly of electric circuit elements, and it has dynamics determined by this Hamilton function. So this Hamilton function involves two fields, so two quadrature fields. What we can call them, there's a field Q and a field phi. Field Q is straightforward. It's the charge density field along this transmission line as a function of x. This is a somewhat more abstract field, this phi field. We use the word flux for it, but it's only, for example, spatial gradients of this field that appear as genuine magnetic fluxes, carried by the inductors of this. But it's straightforward to show that this generates the wave equation of this and actually, is a full description of the dynamics. The one difference, just to mention, the Zurich experiment used not this kind of transmission line, but actually rectangular pipes, so hollow metal pipes. And that's a slightly different kind of transmission line, which can be modeled also in this language, but it involves then also inductances between the top and the bottom. And that adds a new term to this Hamiltonian. So you would add to that Hamiltonian a term which is like phi of x squared. Now I can say that adds a mass to the photon, except I was trying to not say quantum mechanical words. It adds dispersion. It adds a lower frequency cutoff in engineering language, and that's actually not conducive to the story I want to tell, because I'm very interested in this dispersionless setting, which is very easily achieved with a transmission line with two separated metals, and we have many, many such things. I mean, I've checked with the experimentalists, and they'd be very content with having one or two coaxial cables in their pipe, rather than this one square metal transmission line. Okay, anyway, so that's a Hamiltonian. Now, this AWG in this setting will, so you'll choose some pulses to send. Now, what that will do in the language, or to link that thought with the language of this Hamiltonian function, you observe that what what the AWG will want to do is produce voltage waveforms and current waveforms. It delivers both to this transmission line. I've gone to the coordinate x, which means I take a snapshot in time, which is long after this pulse has been launched into the transmission line. So it's like you're in an infinite transmission line at that moment. And then what you can find is that the expectation value of these two quadrature fields, so Q and phi, are simply related through some constants to the thing that you program this device to do, namely to produce a voltage pulse and an associated current pulse. So it's the charge density is directly proportional via this capacitance per unit length parameter. And the phi expectation value is determined by, it turns out, a space integral of the current that's emitted, the current pulse that's emitted by the AWG. Now, now I'm going to quantize. The quantization is normal, field variable quantization. So you elevate phi and q to operators, and they have this commutator, IH bar, and a Dirac delta of the two positions. And now you pose the question, is this device emits radiation? So it emits a state of radiation, and we want to inquire, what is it as a quantum state of radiation? And I would say, initially, I don't know, except it's not likely to be a pure state. It's likely to be a mixed state. There are actually many sort of engineering noise sources that are associated with these boxes. So it's almost impossible that what's initially emitted from the AWG is a pure state, except that whatever state it is, I mean, we'll say it is some mixed state, and it should have these expectation values, because that's what this box is very good at doing. Now, in all of these experiments, the standard step that's performed is that this radiation doesn't go straight into the cold transmission line. It's first attenuated frequently. It's like you put it through beam splitters. So most of the radiation is thrown away. And now you can invoke a well-known fact from optics that if you have any state of radiation, you send it through a beam splitter and you take the little bit that comes out, it's purified. That is a method of getting a coherent state, as a matter of fact, to take a, say, noisy state of radiation. By beam splitting it, you throw away most of the noise. And you can, under some conditions, which I'm not going to mention in this lecture, but if you have enough attenuation, you can overcome the variance, the excess variance, due to the fact that the state is noisy, and then it should be a pure state. And then I would say that, so maybe this is the first sort of assertion about the quantum mechanics of this, that once this pulse has been properly conditioned and is traveling in this cold transmission line, I would assert that it has this pure quantum state. So let me read it out for you. This is the vacuum, and this is a displacement operator. So this is a generalization, or it's a multi-mode coherent state, where it's in general displaced on both quadratures, both phi and q, by some functions, and these functions are related directly back to the expectation values. So the hypothesis is that these expectation values are preserved, no pulse distortion, no dissipation, except for this beam splitting attenuation. So that what's left should indeed be this coherent state. Now, now we know a coherent state is not a single photon state, and this is a multi-mode state, we would say. So, but still, you would like to believe that what's subsequently carried is the usual sort of Poisson distribution of photons with photon number 0, 1, 2, 3. But what photon, you would ask? So this is the question that we posed, and I should have made this equation should be the really big question with a big question mark here. That is, here's this multi-mode or spatial displacement operator with known values of this q of x and phi of x. That is, they're determined by the programming of the AWG. Now, do they indeed correspond to displacement or superposition of a set of states of one photonic state, a state with one attribute. Because you can say, I mean, the usual thing would be to say, well, surely what you should do is take this pulse, whatever it is, Fourier analyze it, and then you get the spectrum of colors, and those are the photons. You get photons of many different wavelengths. But that definitely captures the notion that these photons arrive at a definite time. Because these plane wave modes have no beginning and end. So to capture the idea that a photon arrives in a specific window of time, you should try for some description like this. Now, this seems like a well-posed question. I couldn't, however, find that it had been really directly answered, so we went about answering it. So what do I mean by this? So this is to say that this state should be describable by displacing with one operator, B. So there's B and its Hermitian conjugate, B dagger. They should satisfy normal bosonic commutation relations, and B should annihilate the vacuum. Now, this B is not an elementary field, of course. It's not an elementary operator. It has to be built out of the operators that the field contains. So it should indeed be should be obtained by integrating over these two fields, phi and the conjugate field Q. And the question is, what are the coefficient functions? So that will determine what this theta sub Q and theta sub phi will determine what's the sort of waveform of the photon that corresponds to the voltage waveform that I introduced. And then finally, if I can do that, I want to sort of normalize, so pull out what is beta, so to say things about, well, how many photons are there in this description? Now, we find that with important restrictions, which I'll state on the next slide, this ansatz leads to a unique solution. So there is, in fact, a form, an operator, a specific operator, B dagger, or its Hermitian conjugate B, that satisfies all the rules to be the creation and annihilation operators of a photon. And the answer is sort of halfway just these coefficient functions. That is, note that this is a non-Hermitian operator, so it has a Hermitian and an anti-Hermitian part. This, on the other hand, is a completely Hermitian operator. So by pulling it apart, you're sort of introducing new parts that didn't seem to be there. You're introducing anti-Hermitian parts. So the Hermitian part, once you keep track of the I's, are indeed just these coefficient functions. So the voltage profile is exactly one of the profiles or part of the profile of the photon. But that's only part of the story. There's actually both a Hermitian and anti-Hermitian part, and the anti-Hermitian parts are new objects, so not obvious ones. Now there's already, you see the appearance of these coefficient, these pulse functions, phi and q, but they're inside some transform, and this h sub x is in fact a Hilbert transform. You can say that this has something to do with causality, but it was not sort of the driving principle of this derivation. I'll give examples in a moment of what these coefficient functions actually look like. So there is indeed a solution. It has some strange properties, which I'll illustrate in a moment. The strangeness comes, generally speaking, from this very well-known relation between these quadrature fields, phi and q, and the usual, plane wave quanta of the photons of this field. That it's not that this is a simple Fourier transform relationship. It has these strange factors which are necessary, which are obligatory for field theory to make sense. So square root of 1 over the absolute value of k in this one, and square root of absolute value of k in this one. And they make, especially these pulses which contain many wave vectors, very non-intuitive with respect to these coefficient functions. So Here's, now this is also just to say that, yes, indeed, we can separate things out and also get an expression for the photon number. I've introduced the regular Fourier transform for this, and I'll say a few more words about that. But I emphasize, so that these photons, these B and B dagger, are not of definite frequency. That means they're not eigenstates, or they're not creation and annihilation operators of eigenmodes. But they are creation and annihilation operators that have extremely simple time dependence. They simply translate at the speed of light. So they're, the moral equivalent of eigenmodes, but they do not have a definite frequency. And that's really has to do with the dispersionless nature of this transmission line field. Now, here are a few examples. Well, but first I will make immediately some simplification that I could have made earlier. These pulses could physically be either moving at plus V or minus V. And an arbitrary state of the field, if you set it up at time equals 0, an arbitrary state of the field will have a piece that translates forward and a piece that translates backward along the transmission line. But of course, the AWG only launches a pulse in one direction. So that actually applies or produces a constraint. It means that the current is slaved to the voltage, and they're related by the so-called characteristic impedance of the transmission line. And so it means the AWG does not independently emit a voltage and a current pulse. It emits the voltage pulse, and the current comes along for the ride and has the right value. In that case, these coefficient functions, Q and phi, are both functionals, or simple functions, I should say, of the voltage pulse, one being an integral of it and one being proportional to it itself. The photon number is a little bit simplified, but the condition for this description to be correct is a fairly non-trivial one, which is that the integrated voltage of this voltage pulse be 0. So you call that a bipolar pulse. So a unipolar pulse will not work. What that means is most of the analysis works, except that you get to this, and then you try to extract a coefficient. Well, you find that this product, beta times B dagger, has a diverging commutator with its Hermitian conjugate. So it's not possible to pull out a constant to bring that commutator down to 1. So it can be interpreted in a way to say that if you had a pulse which had a finite average value, it contains an infinite number of photons. And actually, that will mean that it's not secure for QKD. I mean, I can mention the eavesdropper can actually pick you off. And I even worry about that for conventional QKD because they use, of course, very narrow band pulses. So you should think of the field as having many, many cycles, but of course, under some envelope. And if it has a tiny little average value, it probably doesn't have a very big one. But if it does have an average value and it depends on the signal state, in other words, which transmission Alice is going to make, there is actually a hole. There's a security hole, which I don't think has been analyzed very much. Would be a very small one, but not a trivial one though. Okay, so this is showing the entire picture of a particular photon pulse. So I've chosen a voltage pulse, which is this particular, sort of full cosine, one cosine period, but squared off. And it contains, it has 4 parts, just like this expression has 2 parts to make up the coefficient of the phi field, and 2 parts, real and imaginary part, to make up the coefficients of the Q field, and these are the 4 parts. Now, you can extremely roughly look at this and say, this is a cosine, and then its imaginary part, Hermitian and anti-Hermitian part, this is sort of a sine, even and odd functions. And, but this is a very distorted sine. And then this also, this is the integral of this. It turns out that has to do with this expression. So an odd function, and then it's paired with an even function. This even-odd pairing is the normal thing with these Hilbert transforms. For very long wave trains, say this is actually a cosine, then this is very close to actually a sine. And then you say that the waveform of the photon in that case is constant in magnitude. That is, it's cosine plus I sine. So its magnitude is constant in space. We don't talk about nodes of photon states, and we should not actually. Okay, but in this case, they have these very melted forms, but significant and strange is that even though this pulse, the quote physical pulse, is strictly bounded, the voltage pulse, the pulse that's needed, or the functions that are needed to complete it as a genuine photonic creation operator, are not strictly bounded. In fact, they have power law tails, and it's a famous theorem, in fact, of signal processing, Paley-Wiener theorem, that they have to have tails. They have no choice but to have tails. And that stopped me for quite some time with this project, because I said, what does this mean? Is this violating causality or something like that? And I would say the answer is no, and the reason is that a description of these operators is not yet a description of what you have to do to measure them or to cause them to interact with other things. So causality is saved. Just to show that we can do concrete calculations, here for this specific pulse case, you can work out what the photon number is, and I'll try to diagnose this for you. I said Planck's equation is dead, however, it's only slightly damaged. That is, you can take, I don't know if you can see the color coding here, if you take all these factors of this equation, this numerator is indeed the classical energy in this pulse, in this coherent pulse. The denominator, which involves the velocity and size of the pulse, are basically it's h bar over the transit time of the pulse, so it could be called h bar omega. And then there's some funny constant, which is like 3 point something. So up to constants of order unity, this is actually giving exactly what you expect, that the number of photons should be E over h bar omega. So that works pretty nearly, but with constants that you couldn't guess without having done a careful calculation. Let me skip this example because I would like to get on to, discussing the problems of detection. How would you detect a photon in this mode? And okay, this is what's in the paper, but I actually have an interesting story, which I'll tell if I have time, or I may even tell it tomorrow. But I wanted to tell the story of this as a QKD experiment. So remember, this is the schematic of this 30-meter long pipe experiment as currently done. So my suggestion is, on the Alice side, you rip out almost everything. There's a lot of complicated stuff to produce, in fact, entangled single qubit states between the sender and receiver, between Alice and Bob. That's all not necessary here. It is all replaced by simply having two of these AWGs. So I'll do dual rail QKD. So there will be two AWGs. They will feed into two transmission lines, which I labeled B and D, with suitable attenuation. That's what these -20s refer to, and then into the pipe. The Bob side requires things that are, well, easy to state, but difficult to do. But let me just review that. So the scheme of BB84, as hardened by current practice, which involves, say, the decoy technique, involves usually sending a pulse of whatever waveform. Nobody says what waveform it should be. It just says that it should be something which has a state of expectation value, photon expectation value, pretty small. And 0.12 is the recommended size in this dim state BB84 technique. And then you should occasionally send in a decoy with somewhat higher amplitude, and that's for a protocol for catching whether the eavesdropper is trying to do a so-called splitting attack, for occasionally looking for cases where there are two photons rather than one or none. That can all be done in this setting. And recall, BB84 requires 4 possible states emitted by Alice, and here's one of them. She has 2 AWGs, and one of the 4 states is just emit a pulse into the B waveform, into the B channel. The state orthogonal to that is emit the same pulse, but on the D channel. Now there's the so-called diagonal states, the states in between 0 and 1. So 0 plus 1 you get by two simultaneous emissions, pulse emissions from the two waveform generators in phase, exactly identical, but with amplitude reduced by √2. I'll come to the splitter business in a moment. And then the fourth state is just that also with a reversal of polarity of one of the two pulses. So those are the transmission side of BB84. Now it sounds kind of crazy. I'll be finished in 2 minutes. This sounds crazy that, well, this is not a superposition. These two just are two classical uncorrelated signals. However, the key of dim state is you post-select for these one photon state. And the post-selection of this for the one photon state is 1, 0 plus 0, 1. So that is indeed a superposition of the two single photon versions of the B and D pulses. Okay, so that's a legitimate, it sounds like cheating, but that's, they cheat all the time. The sources are in fact classical or, laser sources. What about detection? Well, BB84 says, Bob, at random either inserts or doesn't insert a 50-50 beam splitter to mix these two modes. Of course, beam splitters, you might say, are routine, but that's not true in this case as well. Beam splitting a state of this form is not at all trivial because most beam splitters, including mirrors, are rather bandwidth limited, so they don't work at all bandwidths. 60 years ago, the electrical theorists said there is a perfect solution to this problem. There's a beam splitter based on transformers. I believe I'll pick up the story tomorrow or on Thursday when I lecture again, because this is part of the story of how you make versatile theories of electric circuits, is you should consider transformers. So an in-principle method has been stated years and years ago. It's the so-called hybrid coil. Now, in microwave practice, they have things called hybrids that do approximately this, but this would have to make it more serious. Now, the detector part just says, now measure the photon number. And that's where I get to this, and I'm not going to do it now. So, but it's rather a whole protocol that involves a variety of considerations, and I won't try to do it at my negative time moment. And I think with that, I have given you the whole story for today. Yeah, I'll stop there. I'd be happy to have questions.
Thank you very much. Now the session is open for questions and comments.
No.
So this this AWG, it's a classical device, right? I mean, the AWG.
Well, yeah, in the same sense that a laser is a classical device. Its job is to emit radiation of a certain specification, and indeed, well, it's less quantum than a laser in the sense that, other than emitting radiation with certain expectation values, there's not that much. Well, there is in fact, but there are very non-quantum restrictions on how much noise it should have.
Okay, but otherwise it looks like a very classical, like LC, it's a LC circuit, and then
yeah.
But so to make it really quantum, is it that you just lower the temperature? And,
oh yes, okay. I skipped a few of the comments about that. Yes, of course, it's crucial that it be at low temperature, and that has to do with the fact that a transmission line like this, without any inputs to it, will have Nyquist states. You know, the one-dimensional black body vacuum, black body state, thermal state, and that says that this pulse that you're putting in on purpose has to compete, or there's an additional noise which has to do just with thermal background, and that's actually what restricts you to fairly short pulses. That is, if you make the pulses hundreds of picoseconds long, it turns out it's not likely that there's even one thermal photon in that, say, time window. Short pulses will make it so that at least in that time interval, you have indeed a very pure quantum state. So it's like with these restrictions, you've achieved something that's as quantum mechanical as a state emitted by a laser.
Yes.
Yeah, just wait a minute. I think you just have to stick with it. It has some delay. Hello, hello, hello. No? Okay, another one's coming. Oh, maybe another one.
It's okay? Yes,
Yeah.
it's okay now. Yes, yes. Thank you for your talk, David. I have a question about dispersion. So you say if we put some inductance between the two parts, you have, and is it something which is, because you have dispersion in the experiment, of course.
Yeah.
So the impedance depends on the frequency.
Mm-hmm.
Okay. How does it to take this into account in this thing? Because you have very short pulse.
I would say these kind of old-fashioned microwave transmission lines, these metal pipe ones, intrinsically have a lot of dispersion. So are ones you would only use or only do use in a pretty narrow bandwidth setting. When you have a coaxial transmission line, or actually any two-metal transmission line will pretty much do, it in the simplest description does not have dispersion. And then you ask, well, surely that's not correct. And why is it not correct? It has to do with, for example, if the metals are superconducting, then the conductivity of the metal has a significant kink at the energy band gap, which is at 100 gigahertz. Or the dielectrics will have some frequency dependence. So these are the kind of things that, yes, do give these systems some dispersion. And I would say in this band, it's challenging to get very, very small dispersion, but well, it's something that they can work on. It's something that can be engineered towards if you really care about it. For example, the attenuators, the ones that are used, metal powder filters probably have some attenuation. But it suggests that pure bulk resistive attenuators would actually be better. I mean, so there are sort of detailed discussions of when you would have more or less dispersion. But the model doesn't begin with a big intrinsic dispersion.
Thank you.
Other questions? Okay, so let's thank the speaker again.